Deep beneath the surface of the Earth, in sprawling tunnels that stretch for kilometers, scientists are engaged in a quest to unravel the fundamental secrets of our universe. These modern explorers wield not ships or telescopes, but particle accelerators, immense machines that propel subatomic particles to near light speeds and smash them together with extraordinary energy. The story of particle accelerators is one of relentless human curiosity, technological ingenuity, and profound scientific discovery. From revealing the basic building blocks of matter to probing the forces that govern the cosmos, these machines have transformed our understanding of nature and continue to hold the promise of even greater revelations. The origins of particle accelerators trace back to the early 20th century, a period marked by rapid advances in atomic physics. Scientists had begun to suspect that atoms, once thought indivisible, were themselves composed of smaller constituents. To probe the atom's interior, researchers needed tools capable of delivering particles with enough energy to penetrate its core. Early experiments relied on naturally radioactive materials, but these sources had limited power and control. The invention of the first particle accelerator, the cyclotron, by Ernest Lawrence in 1930, marked a turning point. With this device, charged particles could be accelerated in a spiral path, gaining energy with each revolution. The cyclotron's success opened the door to a new era of experimental physics, enabling scientists to bombard atomic nuclei and observe the resulting transformations. As the decades passed, accelerator technology evolved at a breathtaking pace. Linear accelerators, synchrotrons, and storage rings emerged, each capable of achieving higher energies and colliding particles with ever greater precision. The construction of the Large Hadron Collider, LHC, at CERN near Geneva stands as a testament to this progress. With a ring circumference of 27 kilometers and the ability to accelerate protons to energies exceeding 6.5 tera-electronvolts, the LHC is the most powerful particle accelerator ever built. Its detectors, ATLAS, CMS, ALICE, and LHCb, are marvels of engineering, designed to capture the fleeting traces of particles produced in high-energy collisions. The impact of particle accelerators on our understanding of matter has been nothing short of revolutionary. Through painstaking experimentation, physicists have assembled the Standard Model, a comprehensive framework describing the fundamental particles and forces that constitute the universe. The electron, proton, and neutron, once considered elementary, were revealed to be composites or members of a broader family of particles, quarks, leptons, and gauge bosons. Particle accelerators played a crucial role in these discoveries. The identification of the muon, pion, kaon, and the entire zoo of hadrons in the mid-20th century was made possible by accelerators capable of producing and detecting these short-lived entities. Perhaps the most celebrated triumph of particle accelerators came in 2012, when scientists at CERN announced the discovery of the Higgs boson. This elusive particle, predicted nearly half a century earlier, is responsible for endowing other particles with mass through their interaction with the Higgs field. Its detection required smashing protons together at unprecedented energies and sifting through petabytes of data to isolate its signature. The confirmation of the Higgs boson not only completed the Standard Model, but also demonstrated the power of international collaboration and technological innovation in tackling the deepest questions of existence. Yet, for all their successes, particle accelerators have also revealed the limitations of our current theories. The Standard Model, while remarkably accurate, leaves many mysteries unresolved. It does not account for dark matter, the invisible substance that makes up most of the universe's mass, nor does it incorporate gravity, the weakest yet most pervasive force. The observed imbalance between matter and antimatter, the nature of neutrino masses, and the cause of cosmic inflation all remain open questions. Particle accelerators are uniquely positioned to address these puzzles, pushing the boundaries of energy and precision to search for new phenomena beyond the Standard Model. One avenue of exploration involves the search for supersymmetry, a theoretical framework that posits the existence of partner particles for every known particle. Supersymmetric particles could help explain the nature of dark matter and stabilize the Higgs boson's mass. Although no direct evidence for supersymmetry has yet been found at the LHC, the search continues, with upgrades planned to increase the collider's luminosity and sensitivity. Other experiments focus on rare processes, such as the decay of certain mesons or the oscillation of neutrinos, which could provide hints of physics beyond the standard model. Beyond the frontiers of fundamental physics, particle accelerators have had a profound impact on technology, medicine, and industry. Synchrotron light sources, specialized accelerators that produce intense beams of X-rays, have become indispensable tools for studying the structure of materials, proteins, and complex molecules. In medicine, accelerators are used to generate isotopes for diagnostic imaging and to deliver precise doses of radiation for cancer therapy. Industrial applications range from semiconductor manufacturing to the sterilization of medical equipment. Looking to the future, the potential of particle accelerators remains vast and largely untapped. Plans are underway for even more powerful machines, such as the Future Circular Collider, FCC, at CERN, which could reach energies an order of magnitude higher than the LHC. Linear colliders, like the proposed International Linear Collider, ILC, in Japan, aim to provide cleaner environments for studying particle interactions. Compact accelerator technologies, including plasma wake-field acceleration, promise to shrink the size and cost of accelerators, making them more accessible for research and practical uses. The quest to unlock the secrets of matter is, at its core, a human endeavor, a reflection of our innate desire to understand the world around us. Particle accelerators embody this spirit, serving as both tools of discovery and symbols of our collective imagination. They challenge us to think bigger, to collaborate across borders, and to harness the full potential of science and technology. As we peer deeper into the fabric of reality, guided by the flicker of particles in the void, we are reminded that each breakthrough is not an endpoint, but a new beginning, a step closer to comprehending the ultimate nature of existence. The journey of particle accelerators is also a chronicle of the evolving relationship between theory and experiment in physics. In the early days, theoretical predictions often outpaced experimental capabilities. Concepts like antimatter and the neutrino were proposed to resolve inconsistencies in observations, but their direct detection required technological leaps. The advent of accelerators allowed experimentalists to catch up, confirming the existence of these particles and validating the predictive power of quantum theory. This interplay continues today, as theorists propose new models and experimentalists devise ingenious ways to test them, driving the field forward in a dynamic cycle of hypothesis and verification. The complexity of modern accelerators reflects the scale of the questions they seek to answer. Designing and operating these machines demands expertise in fields as diverse as superconducting magnet technology, cryogenics, vacuum engineering, and data science. The LHC, for example, operates at temperatures colder than outer space, using superconducting magnets to steer and focus beams of protons circulating at nearly the speed of light. Collisions occur within massive detectors lined with layers of sensors, each designed to capture specific types of particles and measure their properties with exquisite precision. The resulting datasets are so vast that they require sophisticated algorithms and distributed computing networks to analyze. International collaboration has become a hallmark of particle accelerator research. Projects like CERN bring together thousands of scientists, engineers, and technicians from around the world, fostering a spirit of cooperation that transcends national boundaries. These collaborations are not only essential for pooling resources and expertise, but also serve as models for addressing other global challenges. The collective pursuit of knowledge, embodied by the operation of large-scale accelerators, highlights the value of shared goals and mutual respect in advancing human progress. Despite the immense costs and technical challenges, the investment in particle accelerators continues to yield dividends far beyond the realm of fundamental physics. The World Wide Web, for instance, was invented at CERN to facilitate communication among researchers, revolutionizing the way information is shared worldwide. Advances in accelerator technology have led to breakthroughs in materials science, biology, and chemistry, enabling discoveries that impact everyday life. The training of highly skilled personnel in these multidisciplinary environments also contributes to the broader scientific and technological landscape, seeding innovations across diverse fields. As particle accelerators probe deeper into the subatomic world, they also provide insights into the earliest moments of the universe. By recreating conditions similar to those just after the Big Bang, these machines allow scientists to study the behavior of matter at extreme energies and densities. Experiments at the LHC have produced quark-gluon plasma, a state of matter thought to have existed microseconds after the universe's birth, shedding light on how ordinary matter emerged from the primordial chaos. Such studies bridge the gap between particle physics and cosmology, offering clues about the origin and evolution of the cosmos. The search for new physics is not limited to higher energies alone. Precision measurements at lower energies can also reveal subtle effects that point to new phenomena. The anomalous magnetic moment of the muon, for example, has shown deviations from standard model predictions in recent experiments, hinting at the possible influence of undiscovered particles. Similarly, the study of rare decays and symmetry violations provides sensitive tests of fundamental laws, offering alternative pathways to breakthrough discoveries. Emerging accelerator concepts hold the promise of transforming the landscape of research and application. Plasma-based accelerators, which use waves of ionized gas to accelerate particles, have demonstrated acceleration gradients orders of magnitude higher than conventional machines. This technology could lead to compact, cost-effective accelerators for both scientific and medical use. Tabletop accelerators might one day bring cutting-edge research capabilities to universities and hospitals worldwide, democratizing access to powerful investigative tools. Public engagement and education are essential components of the accelerator enterprise. Outreach programs, visitor centers, and educational partnerships help demystify the science and technology behind these machines, inspiring the next generation of physicists and engineers. By sharing the excitement of discovery and the relevance of fundamental research, scientists foster a broader appreciation for the value of curiosity-driven inquiry. Ethical considerations also arise as accelerators grow in scale and capability. The allocation of resources, the balance between fundamental research and practical benefits, and the environmental impact of large facilities are topics of ongoing discussion. Transparent decision-making, inclusive dialogue, and responsible stewardship are vital to ensuring that the pursuit of knowledge serves the common good. In the coming decades, the interplay between particle accelerators and other fields of science is likely to intensify. Advances in artificial intelligence and machine learning are already enhancing data analysis, detector design, and accelerator operation. Quantum computing may offer new ways to simulate complex particle interactions, accelerating theoretical progress. Cross-disciplinary collaborations will be essential for tackling the grand challenges at the intersection of physics, cosmology, and technology. The enduring allure of particle accelerators lies in their capacity to reveal the unseen, to make tangible the abstract concepts that underpin our understanding of reality. Each collision, each fleeting particle track, represents a window into the fundamental workings of nature, a glimpse of the forces that shaped the universe and continue to govern its evolution. As we stand on the threshold of new discoveries, the legacy of particle accelerators reminds us that the pursuit of knowledge is a journey without end, fueled by imagination, perseverance, and the unquenchable human spirit. In sum, particle accelerators are much more than mere machines. They are gateways to the unknown, instruments of transformation that have reshaped both science and society. Their history is a testament to what can be achieved when vision, collaboration, and determination converge. The secrets they unlock not only deepen our understanding of matter, but also illuminate the path to future breakthroughs, inviting us to dream, to explore, and to push the boundaries of what is possible.